a quantity is subject to exponential decay if it decreases at a rate proportional to its current value. Symbolically, this process can be expressed by the following differential equation, where n is the quantity and I is a positive rate called the exponential decay constant. The solution to this equation is exponential rate of change. Here n, t, is the quantity at time t, and no equals n, 0, is the initial quantity, that is the quantity at time t equals 0. Measuring rates of decay, mean lifetime, if the decaying quantity, n, t, is the number of discrete elements in a certain set, it is possible to compute the average length of time that an element remains in the set. This is called the mean lifetime, I, and it can be shown that it relates to the decay rate, I, in the following way. The mean lifetime can be looked at as a scaling time, because we can write the exponential decay equation in terms of the mean lifetime, I, instead of the decay constant, I. We can see that I is the time at which the population of the assembly is reduced to 1/e equals 0.3678794441 times its initial value. For example, if the initial population of the assembly, n, 0, is 1000, then at time I, the population, n, I, is 368. A very similar equation will be seen below, which arises when the base of the exponential is chosen to be 2, rather than e. In that case the scaling time is the half-life. Half-life. A more intuitive characteristic of exponential decay for many people is the time required for the decaying quantity to fall to 1/2 of its initial value. This time is called the half-life, and often denoted by the symbol T1/2. The half-life can be written in terms of the decay constant, or the mean lifetime, as when this expression is inserted for in the exponential equation above, and ln(a2) is absorbed into the base, this equation becomes. Thus, the amount of material left is 2 or 1 equals a1/2 raised to the number of half-lives that have passed. Thus, after 3 half-lives there will be 18 of the original material left. Therefore, the mean lifetime is equal to the half-life divided by the natural log of 2, or, for example, polonium-210 has a half-life of 138 days, and a mean lifetime of 200 days. Solution of the differential equation, the equation that describes exponential decays. Or, by rearranging. Integrating, we have where c is the constant of integration, and hence where the final substitution, NO equals EC, is obtained by evaluating the equation at t equals 0, as NO is defined as being the quantity at t equals 0. This is the form of the equation that is most commonly used to describe exponential decay. Any one of decay constant, mean lifetime, or half-life is sufficient to characterize the decay. The notation I for the decay constant is a remnant of the usual notation for an eigenvalue. In this case, I is the eigenvalue of the negative of the differential operator with n, t, as the corresponding eigenfunction. The units of the decay constant are ZA1. Derivation of the mean lifetime, given an assembly of elements, the number of which decreases ultimately to 0, the mean lifetime, is the expected value of the amount of time before an object is removed from the assembly. Specifically, if the individual lifetime of an element of the assembly is the time elapsed between some reference time and the removal of that element from the assembly, the mean lifetime is the arithmetic mean of the individual lifetimes. Starting from the population formula, we firstly let C be the normalizing factor to convert to a probability density function. Or, on rearranging, we see that exponential decay is a scalar multiple of the exponential distribution, which has a well-known expected value. We can compute it here using integration by parts. Decay by 2 or more processes. A quantity may decay via 2 or more different processes simultaneously. In general, these processes have different probabilities of occurring, and thus occur at different rates with different half-lives, in parallel. The total decay rate of the quantity n is given by the sum of the decay roots. Thus, in the case of 2 processes, the solution to this equation is given in the previous section, where the sum of is treated as a new total decay constant. Partial mean life associated with an individual processes is by definition the multiplicative inverse of corresponding partial decay constant. A combined can be given in terms of S. Since half-lives differ from mean life by a constant factor, the same equation holds in terms of the two corresponding half-lives. Where is the combined or total half-life for the process, and are so named partial half-lives of corresponding processes. Terms partial half-life and partial mean life denote quantities derived from a decay constant as if the given decay mode were the only decay mode for the quantity. The term partial half-life is misleading, because it cannot be measured as a time interval for which a certain quantity is halved. In terms of separate decay constants, the total half-life can be shown to be. For a decay by 3 simultaneous exponential processes, the total half-life can be computed as above. Applications and examples. Exponential decay occurs in a wide variety of situations. Most of these fall into the domain of the natural sciences. Many decay processes that are often treated as exponential, are really only exponential so long as the sample is large and the law of large numbers holds. For small samples, a more general analysis is necessary, accounting for a Poisson process. Natural sciences, chemical reactions. The rates of certain types of chemical reactions depend on the concentration of one or another reactant. Reactions whose rate depends only on the concentration of one reactant consequently follow exponential decay. For instance, many enzyme-catalyzed reactions behave this way. Electrostatics. The electric charge stored on a capacitor decays exponentially, if the capacitor experiences a constant external load. The exponential time constant I for the process is Rc, and the half-life is therefore Rcln2. Fluid dynamics. A fluid emptying from a tube with an opening at the bottom will empty at a rate which depends on the pressure at the opening. Thus the height of the column of fluid remaining will follow an exponential decay. Geophysics. Atmospheric pressure decreases approximately exponentially with increasing height above sea level, at a rate of about 12% per 1000 m. Heat transfer. If an object at one temperature is exposed to a medium of another temperature, the temperature difference between the object and the medium follows exponential decay. See also Newton's law of cooling. Luminescence. After excitation, the emission intensity, which is proportional to the number of excited atoms or molecules, of a luminescent material decays exponentially. Depending on the number of mechanisms involved, the decay can be mono or multi-exponential. Pharmacology and toxicology. It is found that many administered substances are distributed and metabolized according to exponential decay patterns. The biological half-lives alpha half-life and beta half-life of a substance measure how quickly a substance is distributed and eliminated. Physical optics. The intensity of electromagnetic radiation such as light or X-rays or gamma rays in an absorbent medium, follows an exponential decrease with distance into the absorbing medium. This is known as the Beer-Lambert law. Radioactivity. In a sample of a radionuclide that undergoes radioactive decay to a different state, the number of atoms in the original state follows exponential decay as long as the remaining number of atoms is large. The decay product is termed a radiogenic nuclide. Thermoelectricity. The decline in resistance of a negative temperature coefficient thermistor as temperature is increased. Vibrations. Some vibrations may decay exponentially. This characteristic is often found in damped mechanical oscillators, and used in creating ADSR envelopes and synthesizers. An overdamped system will simply return to equilibrium via an exponential decay. Social sciences. Finance. A retirement fund will decay exponentially being subject to discrete payout amounts, usually monthly, and an input subject to a continuous interest rate. A differential equation dA dt equals input, output can be written and solved to find the time to reach any amount A, remaining in the fund. In simple glottochronology, the assumption of a constant decay rate in languages allows to estimate the age of single languages. Computer science. The core routing protocol on the Internet, BGP, has to maintain a routing table in order to remember the paths a packet can be deviated to. When one of these paths repeatedly changes its state from available to not available, the BGP router controlling that path has to repeatedly add and remove the path record from its routing table, thus spending local resources such as CPU and RAM and, even more, broadcasting useless information to peer routers. To prevent this undesired behavior, an algorithm named route flapping damping assigns each route a weight that gets bigger each time the route changes its state and decays exponentially with time. When the weight reaches a certain limit, no more flapping is done, thus suppressing the route. See also, exponential formula, exponential growth, radioactive decay. For the mathematics of chains of exponential processes with differing constants, external links, a stochastic simulation of exponential decay, tutorial on time constants,